Hi, this is Scott. I really appreciate our sponsors because they make the show possible. Today's show is sponsored by Developer Express. Become a UI superhero with Dev Express controls and libraries. Deliver elegant .NET solutions that address customer needs today. By leveraging your existing knowledge, you can build next-generation touch-enabled solutions for tomorrow. You can download your free 30-day trial at dx.hanselminutes.com. That's dx.hanselminutes.com.
From hanselminutes.com, it's Hansel Minutes, a weekly discussion with web developer and technologist Scott Hanselman. This is Lawrence Ryan announcing show number 424. In this episode, Scott talks with Len Bass about computer science past and present.
Hi, this is Scott Hanselman. This is another episode of Hansel Minutes, and I'm here at the SATURN conference, at Carnegie Mellon conference here in Portland, Oregon, and I have the pleasure of sitting down with Len Bass, who is a senior principal researcher at the National ICT Australia. How are you, sir?
I'm doing fine. Glad to be here.
Well, I'm glad that I had a chance to talk to you. I've read about your exploits online, and I have actually have a copy of your software architecture book.
Software Architecture in Practice.
In practice. And
third edition.
I think I have the second edition.
Oh, my God. You need to buy the third.
Is it updated with important things?
Yes. I mean, the second edition was 10 years old, and we decided it was time to refresh it. And so the third edition is, I would say, substantially better.
Especially considering today's distributed systems.
So the third edition deals with issues like distributed systems. It deals with issues like the cloud. It deals with issues like programming at the edge. Can't remember offhand what else, but yeah, there was a lot of new material added.
Okay, fantastic. Well, I'll be sure to put a link to that in the show notes so that listeners can take a look at that as well.
Excellent.
So you've moved to Australia now, and you're working as a researcher there, but you did some work in the U.S. that's notable as well.
So I was 25 years at the Software Engineering Institute. I was one of the people that was involved in the software architecture program at the SEI. It may be a little bit of a stretch to say that's the best collection of software architecture work that existed, and I was a portion of it. So yeah.
So you've been in the industry for a long time. You must have a number of stories going back rather far, if I may.
So I got a first job in 1964. When I graduated, I had a bachelor's in mathematics. I had essentially never seen a computer before, and I got a job as a programmer because that's what mathematicians in those days essentially had a choice between it being actuaries and being programmers. For reasons I don't understand, I chose programming, and it seems to have stuck. So one of the stories, and actually this is a story that does have a modern equivalent. One of the stories is the first assignment I was given was to calculate some gravitational effects that involve something called Legendre polynomials. So you don't need to know what a Legendre polynomial is, but it has some factorial on the top and some factorial on the bottom. And you divide the one over the other and you get a number. So it turns out that it took me about 3 months to debug this. The last, I would say, about 6 weeks of that three months was trying to find the same bug. So it was, at the time for me, a difficult bug. And the problem was that I solved factorial. I was a mathematician. A factorial is an integer. You calculate the factorial on the top, you calculate the factorial on the bottom, and lo and behold, in the computer world, the mathematics is finite, and at the time we had 36-bit words, and you got to, I think it was 7 factorial, and it overflowed. So it took me a long time to do that because, again, I'd never seen a computer before. And so I guess there were 2 lessons from that. One is that computer mathematics is finite. You know that. The second message is when you screw up and you're young, it's not your fault. And so we had and that's still relevant. There was a meeting between me and my boss and my boss's boss. And my boss's boss yelled at my boss for not managing me better, for not watching. And so when you're a new employee in a place and just out of school or can plead naivete, then the response is it's not your fault if you screw up. And so I screwed up. It wasn't my fault.
At what point do you think it would be your fault?
Well, so
five, 10 years in?
That's a good question. So these days people get responsibility more quickly than they used to. So I guess I would say it becomes your fault the second time you do it. You know,
fool me once.
Yeah, exactly. And so that was that particular machine was an IBM 7094. And so that was a 36-bit machine. It had 32K words of 36 bits. And that's not 32 meg or anything. It was 32K. And it was a single-threaded operating system. And so the job flow was that you sat down at a key punch and you punched some cards, or maybe you filled out the key punch sheet, which was punched by professional key punchers. One of the professional key punchers had the little finger of her left hand permanently bent backwards from hitting the shift key. So I suppose that would be an occupational hazard. And then you gave the cards to somebody in the operations staff. The person in the operations staff stacked it, read it into a card reader. The card reader was attached to the 7094. 7094, when it was your turn, would read your cards, would process it, would spit it out, and then would generate some printout. And the time for this depended on a variety of things, but typically it was on the order of 2-3 hours. Okay, so
and each card represented a statement?
Each card represented a statement. So at the time it was Fortran, and it was column oriented. Mm-hmm. So columns 1 through 5 were a sequence number, were a label that you could branch to. Mm-hmm. Column 6 was in case you extended past one card, it was the continuation. It meant that the 2 cards represent one single statement. Mm-hmm. Column 7 through 72. God, it's amazing I remember this stuff.
I'm impressed.
Yeah, column 7 through 72 were the text, mm-hmm. and column 73 through 80, and it was an 80-column card, mm-hmm. Was a sequence number. Because one of the things that happens with these cards is you drop them. So you have a program that consists of 100 cards. You drop them on the floor. And it's awfully nice to do programs that where the statements are the order that you intended. And so the sequence numbers were important. There was another technique we used to keep the cards in order, which was you wrote on the top. Which works okay if you have a thick deck. This is better with visuals, but it works okay if you have a thick deck of cards. You can write on top. But when you only have 10 or 20 cards, how do you get enough writing surface to be actually to write it? And the answer is you fan them. You fan them like you would fan a card deck horizontally, and then you would write on it, and then you would squish it up, and it would be a funny-looking font, but you could read it. Mm-hmm. So that was another way of keeping them in order.
The fact that they were each a statement, is that equivalent to a line of Fortran, or would you have a couple of cards represent a line of text in that there were multiple statements per line?
At the time, it was at most one statement per line. Mm-hmm. It could be multiple lines per statement. Mm. So if you wanted to continue, if you had a long one.
And dropping the cards on the ground would be effectively just
reordering
taking your text file and completely randomly reordering.
Yes. Yeah, it's equivalent to that. So one of the interesting things is this took about 3 hours to get a compile error back. So you spent a lot of time desk checking mm-hmm. to try and reduce the errors. You also worked on multiple projects because clearly management didn't want you to spend 3 hours waiting for your turnaround.
That was my question. What are you doing?
Well, during the 3 hours, yeah.
Just hanging out?
No, so you had multiple projects. So what happened is that you submitted something and you waited for the output, and while you're waiting, you moved to your next task, and that's a different card deck, if you will, a different program, and you worked on that. Mm-hmm. And you had several of these, and you would sequence through them through the day. So one of the modern complaints has to do with essentially context switching. So I just heard a discussion and actually participated in a discussion where people talk about troubleshooting a problem.
Mm-hmm.
And one of the thrusts of DevOps is that the people that generated the problem are the ones that are notified immediately, as opposed to going through intermediaries. And one of the consequences of that is you still have fresh in your mind the tasks that you were working on that ended up causing the problem, because otherwise you would have done a context switch and lost context. Well, when you're working on 3 or 4 problems at the same time, in essence, then you're used to doing context switches. And so that was, would have been a funny comment at the time.
Mm-hmm.
Okay, so that's one story.
Well,
Two stories.
let me ask you, if you don't mind.
Oh, sure.
For people, I want to ask a couple more questions about punch cards.
Okay.
If you have a 20, 30, 50 card long application, and then you have to go and debug it, you have the sequence numbers. What happens if one statement needs to become 10? Do you have to go and resequence the entire deck and start from scratch?
No. So first of all, you didn't have to have the sequence numbers. Those were optional.
Okay.
Secondly, there were things you did in terms of sequence numbers. So you would maybe sequence them left to right.
Mm-hmm.
Right to left. So if you sequence them right to left, you can add additional digits without throwing off the sequence.
Mm-hmm.
You could sequence them 100 apart, so that when you added something, it might be, you would add them then 10 apart.
Mm-hmm.
And so there were a variety of techniques that you would use in terms of utilizing the sequence numbers. Mostly, personally, I didn't use the sequence numbers, because it was pure laziness, I guess. You'd have to write them down, or you'd have to punch them in, or whatever. You have to specify them. So there's another story that has nothing to do with computers, but it used to be that telephones were big, heavy devices, and one of the problems with mobile phones is that a whole genre of mystery stories disappears. I mean, I cannot pick up a cell phone, hit you over the head with it, and kill you. Maybe some sort of metal poisoning that would lingeringly kill you, but the old phones were quite substantial and played a large role in a lot of old movies.
Yeah, it seems like in the movies now, if you're going to get bonked over the head, it's with the butt of a gun.
Yeah, exactly.
But back in the day, you hit somebody with a phone, that guy was going down.
Those were heavy Bakelite. Recently, when we moved to Australia, we cleaned out our house and had been there a long time, and we had an old Bakelite phone.
Mm-hmm.
So I showed my grandson the Bakelite phone. He says, "Does it still work?" I said, "Yeah." Had an adapter. We plugged it in. He called his mother and he said, "Mother, guess what? Mom, guess what? I'm talking to you on a real old phone."
I'm calling you from the past.
I'm calling you from the past, exactly.
There was a great video on YouTube recently where they showed some young kids, 8, 9 years old, a rotary phone. And it just was not intuitive to do that at all.
Yeah, so we had to show them how to dial it.
Yeah. We used to joke about how we thought that 911 was a bad idea, because think of all the people that we lost waiting for the 9 to spin
go
back.
around.
It should have been 111 if you really cared about people.
Well, it actually is one. Is it 111 in Australia? Maybe it's 000. I forget. Anyway.
Well, one of those is going to kill people.
So to get back to the stories. So in 1968, I went to graduate school, and I went to graduate school at Purdue University. And in 1967, Purdue opened a new mathematical sciences / computer sciences building. I was a computer scientist. And they had plans to put an IBM 360/67 in the basement. Mm-hmm. So the IBM 360/67 was the first commercially available machine with virtual memory. Let's just say IBM misjudged how long it would take them to build and deliver this system. And so when Purdue opened the building, the IBM 360/67 turned out to have been 3 years away from their first delivery. Mm. So they replaced it with a CDC 6600.
Okay.
So that doesn't sound like such a big deal, except that you have to remember that they wanted the 360/67 in the basement, and the way they arranged for it to get in the basement was they built an elevator shaft to take it down to the basement.
Okay. And these were big refrigerator-sized, multiple refrigerators.
These were room-sized machines, yeah.
Okay.
It turns out that the CDC was 2 inches bigger than the IBM machine, and so they had to redig the elevator shaft in order to make enough space to get the machine in the basement. So these days you get bored waiting 10 minutes for a virtual machine to spin up. So think about having to dig another elevator shaft, and wait for the construction crews and the cement to harden before you can even start to put the machine together. So
let me ask a couple of, and forgive me, ignorant questions about this. These machines that we waited 3 hours for a compile and we waited for holes to be dug to use them, were they faster, as slow as they were they faster than us? And it really was still faster for you to use this than to figure it out yourself with a slide rule and a piece of paper, right? They were more powerful than
They were more
us.
powerful at doing arithmetic type of operations. They were especially useful for repetitive arithmetic type of operations. So the reason you would write a program was not so much that you wanted to do a single calculation. It wasn't like having a calculator where you would type in the numbers. The reason you wrote a program was because you wanted to do either very complicated calculations like the gravity example I gave you,
right,
or repetitive computations. I want to do the same thing again and again and again. And I don't want to have to type in the numbers every time and hit all the pluses and the minuses. It also is less error prone. So if I had a complicated calculation that I had to perform, then I would have had to type in all the numbers and move them around. And actually, that's the story I know, but it wasn't personal. The word computer comes from the way that people used to do computations back when they had adding machines. And so you had a room full of people sitting in front of an adding machine. They would get a card with a number from their left and another card from a number from, let's say, they're up above them. And their job would be to add these two numbers, write it on a card, and pass it off to the person on their right.
Okay.
And those people were called computers. And they ran each program, if you will, twice, because it was a very error-prone process. So that, I believe, that story comes from the 40s or maybe even the 30s.
Wow. Because that's funny that you mentioned that story, because I was thinking to myself, would it have been easier to just find someone with some kind of an eidetic memory, find someone who's some kind of savant, and put him in the basement?
That's probably possible, except even in those days, there were labor laws.
He probably couldn't work 24 hours a day.
He couldn't work 24 hours a day. These machines cost $2 million. So my first job, I got, again, it's funny, I remember these things. I was paid $138 a week.
Sounds like good money for the time.
It was good money. It was more than professors were making it. So I had some friends that were college professors, and I was a fresh bachelor's degree, and I was making more than they were. But the computers cost several $1 million. And so they took better care of the computers than they did of the people. And so, for example, I at one point worked in an unair-conditioned office, whereas the computer was air-conditioned. Well, it got hot. And so then you go visit the computer. You go see how it's doing because it's air-conditioned. You want to see how your program is doing. Have you gotten to me?
Just checking on it,
Just
really.
checking on it, right. So you would hang out there for a while till you cool off, and then you would go back to work. So I gotten so far as Purdue. I did two things at Purdue. One was I was a graduate student doing research in theory of computation. The other, I was a programming. I was an assistant, research assistant, I guess, as a systems programmer in the high energy physics department. So one takeaway from that is these were in two different facilities. So one takeaway is that it's really good to have two offices. So if you have two offices and people can't find you in one, they think you're in the other. And so you always have a built-in excuse for wanting to go lie in the sun or just take time off and go do something else. And at various times throughout my career, I've had two offices, and I've always thought that was an ideal situation.
I think today folks say, I'm working from home.
Working from home, I think, would be the modern analog, yeah. So the computer in the physics department was an IBM 360 Model 44. And it's what these days you would call a RISC computer, in that it did not have a full 360 instruction set, so it needed the operating system it had was very limited. And so my task with one other person was to write a more modern, which in those days meant multi-programming, operating system. And so you ask what I took away from those two jobs. Writing the operating system has lasted a lot longer than the theoretical research that I did to earn the PhD. So there were a couple stories that come from that. One is they were showing me how to use the computer. So there was essentially a power button on the thing, and you had to tell it the date and time. So it didn't have automatic date and time sequence. So the sequence for powering it up was you push the power button, you went over to a typewriter kind of thing, you typed in the date and time, and you hit enter. Not too hard. Okay, so they showed me how to do it. They said, okay, you try it. So I pushed the button, I went over to the typewriter thing, I typed in the date and time, I pushed enter, the lights went out, bells went off, and I'm sitting there thinking, this is a multi-million-dollar machine, what did I do? And it turns out the power had failed at exactly that instance. So it was not my fault. So that's, my standard response to things, it's not my fault. In this case, it legitimately wasn't my fault. So that happened. I don't know what a modern analog of that thing is.
I think the modern analog is my dad we're typing on his computer, and he's finished his great treatise, and he's written his manifesto, and just as his finger comes down hard on the enter key with a satisfying, I'm finished, blue screen of death.
Yeah, okay.
And then he calls me. He's like, I don't know what I did. I just pushed enter. It's not my fault.
It's not my fault.
But you always assume it's your fault.
Yeah, you take responsibility.
Yeah. He was ready to fall on his sword, but I'm pretty sure it's the video driver. Don't think it was you. Could have been you.
So another story. The late 60s was during the Vietnam War era. And so one of the concerns in those days was the United States still had a conscription, still had a draft. You got out of the draft initially from being a student and later from having children. So I got out of the draft because I had children. But others that were graduate students there didn't. And so during that period, there were radicals, not that much different than today. Not so much in the U.S. Well, some in the U.S. run around blowing up things. And there was a computer room at the University of Wisconsin that got blown up. So that caused the administration at Purdue to worry about blowing up computers in Purdue, and so they put what you would call an intrusion detection system in each computer.
And that was a reasonable thing for them to worry about, that a computer might be blown up by a radical?
Well, so the University of Wisconsin was in Madison, Wisconsin, which was a radical sort of place. The Purdue University was in the middle of Indiana, a much more conservative type of place. So the chances of somebody at Purdue blowing up a computer were much less than at the University of Wisconsin. But was it reasonable? It was plausible. Could happen.
And people know computers are $1 million or more, right?
Yeah.
I mean, so if you want to cause damage, you can blow up a dorm, there's $1 million. Or you can blow up a computer, it's smaller, it's still $1 million.
Well, so the reason this particular computer in the University of Wisconsin was blown up was because it was doing defense work. And so it was supporting the war in Vietnam, or at least nominally. So it was a target for being blown up. I mean, in reality, I suspect it had nothing to do with the war in Vietnam, but you can't always choose your targets. And so they put this intrusion detection system in. One of the side effects of using punch cards is that they generate a lot of dust. As every time you put it through a card reader, a little bit gets scraped off, it generates dust, and so there's a lot of dust in the environment. And so one of the preventative maintenance activities that one would perform is to have the IBM repairman come in and vacuum out the console. So the intrusion detection system was attached underneath the console, and it was a silent alarm in the sense that you could push it and the intruder wouldn't know about it. So the repairman is lying on his back. He's got his screwdriver in his hand. He's taken off the panel to get to the innards of the computer. He can't remove the panel because there's this thing in his way. And this thing was the intrusion detection system. So he unscrews the thing, which sets off the silent alarm. He's sitting there with his vacuum cleaner going about his business, lying there with his vacuum cleaner going about his business. And all of a sudden, the riot squad shows up in full riot gear with sawed-off shotguns, pointing at this guy lying on the floor, saying, "What are you doing down there, fella?" So I guess, for a modern analogy, it's, intrusion detections have false positives, and you need to worry about false positives as well as real positives.
There's a great cartoon called XKCD. I'm sure you've probably seen them, the little stick figure guys. Mm-hmm. And a mother gets called by the principal at the child's school and says, I wanted to talk to you about your son. Is it true that his last name is Tables, drop? and are you sure that's his last name? And she's like, oh yeah, little Bobby Tables, we call him. And the principal says something like, well, I think Bobby's been up to some mischief lately. And the mother's like, well, maybe you should sanitize your database inputs.
So that's another story. It brings to mind another story. There was a time in this era, computers were centrally managed, and so there was a computer for the computer room, for the campus. The Cornell University wanted to cleanse the material that went through their computer, and so they had some list of forbidden words. There was a faculty member named Fink.
Uh-oh.
Yeah, you see where this is going, right? There was a faculty member named Fink who was unable to get any jobs through the computer center. And so finally they diagnosed it and figured out because he was on the list of forbidden words. And so I presume then they relaxed some restrictions. I don't know. But again, this is a security kind of issue, or a privacy sort of issue, I suppose, these days.
These false positives, they'll get you every time.
False positives are a problem. And in general, in the modern world, every time something goes wrong, in, let's say, the cloud, there's a bunch of data that has been gathered from various monitoring and logging systems, and diagnosing that is an art. And one of the research activities is okay, let's build a variety of automatic diagnostic tools that can look at these sorts of outputs and generate diagnosis diagnosis. And the problem with them is both false positives and false negatives. No one has been able to satisfactorily find algorithms that don't generate false positives, and false positives are like crying wolf. Mm-hmm. And so then no one pays any attention to the real positives, or false negatives, which means something went wrong and I didn't even notice. And so that's an active area of research, and B, a good thing to work on.
I was at a hackathon in New York, and I was basically setting up about 100 young women to get onto the cloud, and they were signing up for the cloud, and everything was working out great. And after about the 30th one, they all started getting denied. They thought it was a denial of service attack because their systems couldn't imagine 100 people from a single IP address deciding to sign up at the exact same time. So we got blocked.
Yeah.
Made the entire hackathon, and of course makes the product look bad. Everyone feels really guilty. And I had to go and call and say, you guys need to unblock this IP address,
it's
which
legitimate.
is a big deal.
Yeah.
Right? To whitelist us for now.
Yeah, it's legitimate. And there are a number of security-related types of activities that generate false positives, and so on. One thing I learned I heard it the second time at this conference. One of the things that organizations do to sensitize their employees is they send out their own phishing expeditions. So it turns out that the biggest security problem these days is primarily phishing. Mm-hmm. That's where most of the break-ins originate, not exclusively, but an awful lot of them. And so what organizations do is they will phish their employees. Mm-hmm. And what happens when you click a link is that you get some sort of what's the reverse of an attaboy,
Well, you've been pwned.
Yeah, okay, you've been pwned. That phrase I hadn't heard. So that you get some sort of response saying this is bad, don't do it.
Yeah, absolutely. We actually, I used to work in banking, and we were warned that picking up stray USB keys from the parking lot and then taking them in and plugging them into your computer was extremely bad idea. And we had always theorized that that would be a brilliant way to do kind of information warfare. You just fly over an important place, drop 1,000 USB keys into their parking lot, and then just simply wait for the bad guys to pick up the keys and plug them into their computer.
So are you familiar with Stuxnet?
Is that how we did that?
That is how we did that. Well, that's how that was done.
I didn't do it.
Yeah, I didn't do it either. Yeah. And so at least the theory, the conjecture is that the virus was introduced to a network which was off the internet, so they couldn't do it directly, through a USB key that was or a memory stick rather, that was inserted into a USB port. Many organizations epoxy the USB ports on the computers that they hand out, just exactly for that reason.
Oh wow! Just cover it completely. Physical security.
Physical security, yeah. So I mean, security itself is a multi-layered, multifaceted type of activity, and there's physical security, there's organizational security, there's technical level of security. So that's one of the areas where there's an interplay between what the organization does, the processes they use, and the architecture that you design. Continuous delivery, which is my current I don't want to say passion because I'm too old to be passionate, but my current active area of interest is another one. So there are a number of problems. So continuous delivery is a process whereby the developers commit code and it automatically goes into deployment or into production. And there are problems that come up doing that, and the problems can be solved either by improving the process, yelling at the employees, by improving the architecture, making it resilient, or improving the tools that you use to move through the deployment chain. And so solutions consist of interplay between the three of those, and you can trade off. So mostly when we talk about trade-offs, we think about trading off one runtime property against another runtime property, or maybe a runtime property against a development time property. But you can also trade off or make decisions as to where activities get done and how long and how they get achieved. And so you can either solve some problems with architectural means, you can solve some problems with tooling, you can solve some problems with process means, or all three.
Mm-hmm. It always seems like the issue of people is what it comes down to. People will mess it up. If the computers have been told what to do correctly, it's going to be someone making a mistake, whether it be social engineering or phishing or pushing the wrong button.
Well, I guess so. You can design systems so that it's harder to make mistakes. So that's a human factors kind of issue. You can design the tools so that it's harder to make mistakes in terms of input. You can design the tools so that they verify the input. So again, there are a variety of different ways that solutions can be achieved. And as not a software engineer, but as a system engineer, I mean, that's part of your task is to decide on what is the most appropriate and cost-effective method of solving particular problems.
And do you cover some of these things in the latest release of your book?
So I'm actually in the process of writing a new book, and I'm using social media to get feedback on it. So the new book is called DevOps: Software Architect's Perspective. So if you're at all interested in DevOps, there's a lot of material that talks of, so DevOps is a movement which is intended to make operations people first-class citizens as far as software developers are concerned. So they have requirements. Then their requirements should be fed in at the front end, just as the business-facing requirements should be. And there's a lot of material on the IT perspective of this from the operations people. There's a good book by Jez Humble, and the other author will shoot me because I can't remember his name.
Fowler?
No, but it's another ThoughtWorks person.
Yeah, I had Jez Humble on the show talking about continuous delivery recently.
And so that's the book that gives the world from the project manager's perspective. Okay, so what is DevOps from a project manager's perspective? And to me, there was a perspective missing, which was the architect's perspective, which is how do you design these things? Well, I'm a software architect. I'm told that I need to learn about DevOps, or I need to use DevOps in my current job. And, what is it? How much time do I want to spend doing research? It's a lot of work. And so I decided that was a gap that needed to be filled. And I volunteered myself and two of my colleagues at NICTA to fill it. So we've been writing a book. So when we've written the other books, the process is you write the books, you keep it to yourself till you have a first draft. You send it to the publisher. They send it out for review. You get comments back. It's a very, A, time-consuming, and B, a limited set of review comments.
Well, and arguably it's the opposite of continuous delivery.
Yes. Or at least incremental delivery.
Indeed.
And so for this book, we're doing a different thing. We are publishing the chapters as we complete them on SlideShare. And people are welcome to send us comments. We've gotten some comments, some feedback. Some people just say they like it, which is nice to hear, but doesn't help us improve it.
Okay.
And so we have 6 chapters out there at the moment. The book is projected to be, I forget. Well, it depends how many case studies we have. So there are, let me say, 10 or 11 chapters of material and ideally 4 chapters of case studies. We've released 1 chapter of case study. We have another one where we have, I think, negotiated with a company to be the case study.
Okay.
And we're releasing them 1 chapter at a time. And the book is, I would say, half done, and we will have the first draft complete by the end of the year.
So where can I send people where they can give you feedback?
So SlideShare collects feedback. So SlideShare has an option for comments. When we do a new chapter, I post it on LinkedIn. Okay. So you can put comments. Most people put comments on LinkedIn, few on SlideShare.
Okay. Well, I'll collect the links from you, and we'll put them in the show notes to send people directly to read the current chapters and provide feedback directly.
Yeah, so we have a website that links to the current chapters. It has the outline and the preface and some other material, but it provides links to the current chapters. So, yeah, I encourage people, A, to read it, and B, to send us comments.
Fantastic. Thank you so much, Len Bass, for chatting with me today.
It's been my pleasure.
This has been another episode of Hansel Minutes, and we'll see you again next week.